All right, Chemistry 1411. Continuing on with the practice ACS style exam. There we go. We're going to take a look at question number 20 right now. So this is question 20. It says, what volume of 0.2 molar potassium oxalate is required to react completely with 30 mils of 0.1 molar iron 3 nitrate? And here's the balanced equation they give us. So let me write it down, and that'll help you get an idea of what's really being asked here. So you have 2 moles of iron 3 nitrate plus 3 moles of K2C2O4. So that's potassium oxalate, which produces iron, so this would be iron 3 oxalate. There we go. Plus 6 moles of KNO3, potassium nitrate. And what they're telling us is that you're starting out with 0.0300 liters, right? Because 30 mils is that many liters of 0.100 mole per liter, or 0.1 molar iron 3 nitrate. And it's asking you what volume of 0.200 molar potassium oxalate is required to react with all this. So we need to figure out the number of moles of potassium oxalate, right? Because if we have concentration, right, if concentration molarity is equal to the number of moles divided by the number of liters, right, we can figure out the number of liters. We can say the volume is going to be equal to the number of moles divided by the concentration, like that. Okay, and that's going to be the last thing that we'll do. But right now, we need to figure out the number of moles of K2C2O4, potassium oxalate. So let's get some work going here. The first thing I'm going to do is I'm going to figure out the number of moles of iron nitrate, iron 3 nitrate that I'm starting out with. So I'm going to do this calculation, and you end up with 0.00300 moles of the iron 3 nitrate. Well, let's plug all this into some dimensional analysis here. If I have 0.00300 moles of the iron 3 nitrate, okay, and from my balanced equation, I know that for every 2 moles of iron 3 nitrate, I consume 3 moles of potassium oxalate. Okay, if I was to stop right here, this would cancel, and I'd end up with the number of moles of potassium oxalate. Let me fix that. I'm getting carried away here sometimes. I'm so excited about solving the problem. So that would give me the number of moles of potassium oxalate, but I have the concentration of the potassium oxalate, don't I? Right? I have that here. So I know that I have 0.200 moles of potassium oxalate, K2C2O4, in every 1 liter of K2C2O4. Now I'm running out of space here, so I'll stop right there. And I end up with 0.0225 liters as being my final volume. Well, if I take 0.0225 liters and I multiply it by this conversion factor, in 1 liter there's 1,000 milliliters. I'm going to end up moving the decimal place over 1, 2, 3 places, and I end up with 22.5 milliliters as being the volume required. That's answer C. Now notice again that all the answers are in milliliters, and that's why you have to do this conversion factor at the very end. Give me a thumbs up if you think you could do that one. And if you have a question, stop me. Feel free to stop me at any point along the way here, and I'm happy to address a question that you have about these. These are important problems. You notice that out of these first 20 problems, there's been several stoichiometry problems, right? Looking at molar ratios and relationships, being able to understand how to use a balanced equation. But normally, if my students have gotten to this point in the class, you know, we looked at enough ice tables in general chemistry too, where we had to apply stoichiometry, that students are usually pretty solid on this. by the time we get here. Well, let's take a look at a molecular geometry problem. Oh boy. Question just asks us, how many lone pairs on central atom, which it doesn't tell us what it is, central atom of ClF3. First thing we're going to do is we're going to figure out the total number of valence electrons. So chlorine has 7 valence electrons. Fluorine is also a halogen. It's got 7 times 3, so that's 21 plus 7. That gives us a total of 28 valence electrons. Now, if you remember, when we drew Lewis structures and then determined molecular geometries after, let's just worry about the Lewis structure for now. Hopefully you remember a couple of rules. First of all, it's usually that the least electronegative element ends up in the middle, or sorry, in the center as the central atom. Not all the time, but most of the time, okay? So that would place chlorine in the middle. Now, another reason why chlorine is going to have to be the central atom is because fluorine can only ever form one bond and have 3 lone pairs, no exceptions. So that means that we're going to have to start like this. With our chlorine, we're going to have to draw 1, 2, 3 bonds to fluorine, and then we have to fill up the octets of all of the fluorine atoms like that. Now, how many electrons have we used up thus far? We've used up 8 times 1, 2, 3. That gives us a total of 24 valence electrons. If you take 28, subtract 24, that gives us 4 valence electrons left over. Where are they going to go? They're going to go on the central atom. They're going to go on the chlorine, like that. Now the chlorine is exceeding an octet, but that's okay because chlorine is in period 3. It can exceed the octet rule. Also, you can double check the formal charge on the chlorine. Chlorine has 7 valence electrons, subtract 3 sticks and 4 dots. That gives it a formal charge of 0. So everything is good about this Lewis structure. So how many lone pairs do we have? This is a lone pair, and this is a lone pair. Therefore, we have 2 lone pairs, which is C. 2 lone pairs on the chlorine in ClF3. Let's move on to question 22. It says, how many sigma bonds and pi bonds are in this molecule? Oh, this one's a tough one to answer on Microsoft Teams, but I'll do my best. I'll redraw the molecule for you here. Just give me a couple seconds here to duplicate this. And I'm not going to use bond line structures. I know we went over them in class in dirty detail this semester, but I'll just draw the entire Lewis structure because I love writing out Lewis structures that are humongous. No, I don't. Okay, there's that. Then we have the alkyne over here. That. And we have this carbon here. There we go. So that's the molecule. We're trying to figure out the number of sigmas, and we want to know the number of pi bonds. Well, remember that any bond after the first bond is considered a pi bond. So if we wanted to isolate all of the pi bonds, remember it's anything after a sigma bond. So this is a pi bond, right? This is a pi bond, this is a pi bond, this is a pi bond. And over here we have 1, 2 pi bonds in that triple bond, right? Because anything after the first bond is considered a pi bond. So that gives us a total of 1, 2, 3, 4, 5, 6 pi bonds. So we'll slap the number 6 over here. Now for the sigmas, it's going to be a little more complex, isn't it? I'll erase the markings that I had for the pi bonds to simplify things. So I'm going to try not to botch this, but what if we use the highlighter? Will that work? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Did it. Okay, so there's 21 sigma bonds. That's one of those things where you might want to double check it, a couple of times just to make sure you're 100% correct. But that is answer D, is where we have 21 sigma bonds and 6 pi bonds.